Welcome everyone to our solar photovoltaics course. So far we are discussing about different varieties of the solar cell. If you remember, we have started with silicon solar cell, especially the crystalline silicon solar cell, and then we moved to the amorphous silicon solar cell. And finally, when we are discussing about different third generation solar cell, first we started with dye sensitized solar cell. And we have seen that using some semiconducting material like titanium dioxide and some absorber which can absorb the sunlight, we can make also in a very simple structure solar cell, namely dye sensitized solar cell. Now, there are different varieties of the solar cells are possible, but if you look all different kinds of solar cell, they have the similar kind of structure. They have a cathode, anode, and in between them there is a sandwich layer. Now, the sandwich layer which is actually made of this which sometimes called the active layer also, that actually changes from solar cell to solar cell. For example, if you take a silicon solar cell, then a PN junction diode, like so PN N type semiconductor is the active material there. If you go to organic solar cell, then the donor polymer and the acceptor small molecule, they are the active layer. If you go to dye sensitized solar cell, then semiconductor like titanium dioxide or zinc oxide and the dye molecule like ruthenium based dye, they are the active layer. If you go to perovskite solar cell, it is the perovskite who forms the active layer. Now, in the context of the organic solar cell, we have seen that we can make an organic solar cell in two different ways. And to make an organic solar cell, we need two different materials. One is a donor material where actually the exciton generation happens, and an acceptor material which helps to dissociate the exciton into free charge carrier. Now, this donor and acceptor material, we can arrange them in two different ways. Either we can put them layer by layer, like we can put a layer of donor material and then put another layer of acceptor material, and then we can follow this same procedure again and again to build up multiple layers. Or what we can do is we can mix that donor and acceptor together in some common organic solvent, and from that mixture we can make the solar cell. Now, the first type of solar cell was called layer by layer solar cell, and the second type of solar cell was called bulk heterojunction solar cell. Now, we have also seen that this bulk heterojunction geometry is much preferred geometry in comparison to the layer by layer geometry. Now, in the context of the organic solar cell, when we use a organic polymer, one of the very well known factor associated with a organic polymer is that their small exciton diffusion length. Now, this conjugated or conducting polymer have an exciton diffusion length of 10 nanometer. So, that means the electrons and holes can travel only 10 nanometers before they recombine with each other. Now, consider the case where we mix a polymer with a small molecule. For example, you can take a very well studied polymer, poly-3-hexylthiophene or P3HT as a donor polymer, and a very well studied small molecule like PCBM, which is a fullerene derivative, and you mix them together to make the active layer for the organic solar cell. But this organic polymer, they have a core which is electron rich, and they have a side chain which helps to solubilize them. Now, most of the time this side chain, they dangle outside the core, and that prevents the efficient interaction between the donor and acceptor. Now, people were thinking how to circumvent this problem, how to overcome this small diffusion length problem of the organic solar cell. See, like if the electron can travel only 10 nanometer before they recombine, so that means the two electrode has to be in a length scale of 10 nanometer, because beyond that distance, whatever the exciton generated or whatever the free charge carrier generated, that will not contribute to the current. And that is why you always see that the thickness of the organic solar cell is much less than the silicon solar cell. Now, scientific community were thinking about that, how to solve this problem. Now, inspired by this inorganic self assembly of the nanosphere, people are thinking that is it possible, starting from a macro polymer, whether we can make a size tunable organic nanoparticle and self assemble them, where only the electron rich core of the polymer will be exposed to the outside and the side chain will be dissolved or solvated inside, so that the efficient interaction between the polymer and the small molecule will be possible, and also the diffusion of the electron within that certain length scale is possible, so that the electron can easily reach to the electrode before reaching the or before recombine with each other. Now, that gives the concept of this organic solar cell. In today's lecture, we will discuss about in details what is an organic solar cell or organic nanoparticle based solar cell, how to fabricate an organic nanoparticle, what are the possible application of the organic nanoparticle, and how we can characterize this kind of nanoparticle. Okay, let us have a look. Now, the outline of the today's talk, first we will discuss about the organic nanoparticle based solar cell, especially the essence of that solar cell and the different preparation and synthesis method. You can make it either by physical method or by chemical method. So, we will discuss about that. Then some of the excellent properties of this organic nanoparticle solar cell in comparison to their bulk counterpart. Finally, what are the possible applications of these organic nanoparticles? These have been used in solar cell, these have been used for making LED, they have been used for making different kind of detectors as well as the lasers. And the future outlook, like how we can go to high efficiency organic nanoparticle based solar cell. Now, organic optoelectronic devices like organic solar cells and organic LED has attracted significant research interest due to high figure of merit, scalability as well as flexibility. Now, this flexibility is one of the major issue with the inorganic optoelectronics devices. Let us say I wanted to make a solar cell which I can paint or which I can fix on my top of my college bag. So, that is not possible with a silicon based solar cell, because the substrate is not flexible, it is rigid. So, I cannot give it an arbitrary geometry. But if I use a plastic substrate which can conduct the electricity, then I can put it on any substrate. I can put it on a clothes, I can put it on any fabric, I can put it on a bag. So, that kind of flexibility the organic conducting polymer offers us, and that revolutionized the field of the organic optoelectronics devices. And they are scalable, that means you can make it roll to roll, and also the figure of merit or the performance is tunable. So, because of that, there was a tremendous amount of research was devoted for developing new materials which can be used for organic solar cell, organic LEDs, and finally organic nanoparticle based optoelectronic devices. Organic photovoltaics are advantageous for their reduced cost and high flexibility, the two factors we have already mentioned. Now, many times the organic materials are less inexpensive in comparison to their inorganic counterpart. One of the major reason behind is that you can make organic materials in a solution fabrication technique. But if you have seen that when we make a silicon solar cell, we have involved very high temperature furnace which goes beyond 1200 degrees centigrade. Now, maintaining this high temperature is always very costly method, whereas like this organic solar cell or organic nanoparticle solar cell, you can make it by a solution based approach in a roll to roll basis. So, that reduce their cost. But of course, it is true that some of the organic materials itself is most costly than the inorganic material. Photophysics and morphology in nanoscale in these devices play a significant role to control their performance and can be optimized. So, this factor we have discussed earlier also, like whether we have an organic solar cell or whether we have a dye sensitized solar cell, the self assembly or the assembly of the different active layers, that plays a very vital role in the charge conduction and charge carrier mobility. Now, these organic polymers, when you self assemble them, what is their nanomorphology or at the nanoscale, how does the charge transfer dynamics changes, that play important role in determining their efficiency and their different kind of output characteristics. Now, what is the origin of this problem? We have already discussed little bit. Now, again go back to our this favorite formula of the efficiency. We know that the efficiency of any solar cell, that depends upon 4 factors, right. One is the exciton generation, that means how good is my material. Second is the exciton dissociation. So, excitons are the bound electrons and holes, but for the charge carrier we need a free charge carrier, we need a free electrons hole which can travel to the 2 electrodes. So, the bound exciton needs to be dissociated. So, that is why the second step in this process is the exciton dissociation, followed by the exciton diffusion. Now, once the exciton has been dissociated or the free charge carrier has been generated, then those electrons and holes needs to be travel or needs to be percolated to the 2 different electrodes, that is called exciton diffusion. And finally, once those electrons and hole has reached to the electrode, they needs to be collected or they needs to be extracted by the electrode. So, that is called charge collection. So, there are 4 processes: exciton generation, exciton dissociation, exciton diffusion and charge carrier collection. And we have said that this 4 process is a additive function or it is a product function. So, that means each and every phenomena or each and every process is dependent on each other. For example, like let us say I have a very nice material which can absorb the light very well over the all spectrum and whose absorption coefficient is very high, but after generation of the exciton we do not have sufficient exciton separation. So, they remains in the bound state. Then what is the advantage of making this high number of excitons? Now, the second step, even let us say all the exciton has been now separated, but I have a very poor morphology in the devices. So, what will happen? All those charge carrier, although they have now separated, they are free charge carriers, they cannot travel to the electrodes. So, they have get lost. So, that will not contribute to any effective current. So, that is also not a good scenario. And finally, the interface between your active layer and electrode also play a very crucial role. So, let us say the morphology is very good, you have a very good fill factor, all the charge carrier has reached to the electrode, but the energetics between the electrode and the active layer or the interface between the active layer and the electrode is such that electrode is not capable to extract those charge carrier. So, that is also not a good scenario. So, to get an optimum scenario, we have to optimize each and every factor equally rather than optimizing one factor to the maximum and neglecting the other. So, that is why we call it as a product function, not a additive function. Okay. Now, in the context of the organic solar cell also the same thing, the first stage is exciton generation. Now, if I have to have a good exciton generation, that means I need to generate more and more charge carriers. So, for that what should I do? We should make materials which can absorb the light over a broad electromagnetic spectrum. That means we need a material with a lower band gap, that is called low band gap polymer. Now, these are some of the example of the low band gap polymer which people have synthesized, and you can see that they have a structure, chemical structure like this. Now, these materials like they are very good to absorb the light and their absorption coefficient is also very good. That was the first step. Now, the second step was exciton dissociation, and this polymer, when they generated the excitons, now we bring an acceptor molecule very close vicinity to the donor material, so that there is an electric field or electric potential generated at the interface, and that potential helps to dissociate the exciton into free charge carriers. So, here the donor is a conjugated polymer, and after the light absorptions what will happen, like this is the HOMO level which is completely filled, and this is the LUMO level which is unoccupied. After the light absorptions what will happen, the electrons will go to the LUMO level and hole will remain here. The second stage in this process is exciton diffusion. So, now I have a donor excitation which will be followed by a diffusion of the exciton to the acceptor material. We are using PCBM as an acceptor material. Now, the energetics or the positions of the energy level such that the PCBM HOMO-LUMO energy level lies exactly in an ideal position in comparison to the conducting polymer or conjugated polymer which we are using in this study. So, that the electron can inject from the LUMO level to the LUMO level of the PCBM, and hole can inject from the HOMO level of the donor molecule to the HOMO level of the acceptor molecule. And this difference, you see this difference, the difference between the LUMO energy level of the acceptor and the HOMO energy level of the donor, this difference is called the open circuit voltage, VOC. So, the open circuit voltage comes from the difference of the LUMO energy level of the acceptor and the HOMO energy level of the donor. So, now exciton has been dissociated, electron is now here and hole is now here. Now, we have, so now we do not inject here, let us consider that although we say that we have injected the hole, so that is a possibility, but when the exciton dissociation happens, electrons only inject and hole still remains here. Okay. So, electron is now in the acceptor and hole is in the donor. So, the two electron or the two charge carrier has been now separated. Okay. Then the third process is that here this is the charge after the exciton dissociation is happen, then what it should be happen, the exciton diffusion or charge transport. So, towards the polymer, the donor, the hole will travel to this side and electrons will travel to the acceptor molecule. Now, for doing this process to be optimum, what we need? We need an ideal morphology. We need that donor phase, where this is the donor phase, and the acceptor phase, which is this phase, they are separated with each other. So, this is the hole which exists in the donor phase, and this is the electron which exists in the acceptor phase. Okay? And you can see from this image, which is a kind of block diagram. So, the donor and acceptor, both of them are distinctly phase separated. We can see clearly the donor phase and we can see clearly the acceptor phase, and also this forms a phase separated bicontinuous percolated network. So, that means not only the phase separation, you see that the phase separation is bicontinuous. I have donor phase, acceptor phase, then I have again donor phase, then acceptor, donor, acceptor. So, it is a bicontinuous separation, and the charge carrier can travel using this network. So, that is why this is called a phase separated bicontinuous and percolated network. So, whenever we talk about an optimum morphology in an organic solar cell, basically we mean a phase separated. So, donor phase and the acceptor phase should be separated, bicontinuous, they will be repeated, and percolated network. So, that means the electrons and hole can travel using this percolated network. So, by an ideal or optimum morphology, we mean a phase separated bicontinuous and percolated network. So, that was our third step, that was our exciton transport or exciton diffusion or free charge carrier diffusion. Now, no longer the exciton exists, because now we have let us say 80 or 90% exciton has been dissociated to the free charge carriers, and they are now moving along the electrodes. Now, here is the problem. When the exciton diffuse or when the charge carrier diffuse, we know that the 10 nanometer is the exciton diffusion length. That means electron can travel only 10 nanometer before they can recombine with hole. But let us say I put an electrode on this side and I put another electrode on this side. So, what will happen? So, the electrons whatever have been, or the holes which have been generated here, so they have to travel along this distance or they have to travel along this distance to reach to the electrode. But if, and this distance let us say 100 nanometer, but the electrons can travel only 10 nanometer. So, that means, so only 10 nanometer the electron can travel before they will recombine with hole. So, then this, if the thickness of the active layer is 100 nanometer, then only those electrons and hole within which is along the 10 nanometer distance scale from the electrode, they will contribute to the current. The remaining thing which is in the bulk, they will not contribute to the charge conductions. So, that is not a good scenario. And to prevent that thing or to circumvent that thing, we came across with this organic nanoparticle concept, and we have been inspired by the inorganic nanoparticle assembly. So, we have seen that how the sodium chloride or how the inorganic nanoparticle system self assembled. Now, the stable heterostructure can be obtained in a single step through self assembly of sphere. Let us say, like, what do you mean by self assembly? Let us say I have a red color sphere and I have a blue color sphere, okay, and these two sphere, and I have a, like, some kind of floor, and I allow you to pour this red sphere and the blue sphere, or red ball and the blue ball, to, like, pour on the floors. Now, there are plenty n number of different ways you can place the different colors balls on the floor. I can just arbitrarily drop first the red color ball followed by the, like, blue color ball. So, what will happen, like, according to their potential energy, red color ball will be, like, placed in certain location and the blue color ball will be placed in certain location. Now, if I do not follow any strategy, or if I do everything in a very arbitrary way, so if I pour, let us say in a 10 by 10 room 1000 red color ball and 1000, like, blue color ball, so they will be, like, arbitrarily oriented. So, it might happen that one blue color ball is sitting on one red color ball, or one red color ball is, like, sitting on a blue color ball. So, we cannot control their arrangement, and that is, and if you explain this in terms of the scientific phenomena, you call it that depending upon their potential energy or depending upon their free energy, so they assemble with each other. Now, this kind of assembly which is not driven by any kind of external force, that is called a self assembly. Now, this was the example of a macro system or a macromolecular system or a bulk system. Now, what will happen, the same thing if you go to the nanoscale. Now, this football, this red color ball and the blue color ball, let us say instead of a football, they are now 10 nanometer scale red color sphere, nanosphere, and 10 nanometer scale blue color sphere or blue color nanosphere. Now, instead of a 10 by 10 meter square room, now you consider you have been allowed to arrange those different colors balls on a 100 nanometer square area. So, now the question is that how this red color ball and how this blue color nano ball they will distribute on this area. So, again they will distribute according to their potential energy or according to their surface energy, but we have learned that whatever the physics which govern the motion of the particle in a macromolecular or bulk system, that the same rule does not apply when you go to the nano system, because like the smallness of the system prevent us to use some of the very common laws of Newton's or the classical kinematics law to use there. So, now even those nanoparticles or the nanosphere will self assemble with each other. Now, if the nanosphere one of the advantage in the case of the nano system in comparison to the bulk system is that here you can actually have a control over the arrangement of the systems in comparison to a bulk system. In a 10 by 10 meter square room, if I drop like 1000 red ball and 1000 blue color ball, so I do not have a control how they arrange each other. But in a 100 nanometer square floor, if I have like 10 nanometer red ball and 10 nanometer like blue ball, then I can control the way of their arrangement, and that external control actually is tuned by the internal self organizations of this particle, and that is the beauty of the nanosystems. So that so what is the advantage of that? First of all, like if you can change the diameter or the size of this nanosphere, then you can change the way they arranged. You can change either the red to blue ball diameter ratio, or you can change the ratio of the all the like red ball keeping the blue ball same, or you can change the diameter of the blue ball keeping the red ball diameter same. So, all of these things will contribute to defined self assembly. So, that is, and in each and every case we will get a very stable structure or stable nanostructure. So, the stable heterostructure in a single step through the self assembly of the sphere can be obtained in an inorganic system. Tunable packing geometry of semiconductor assemblies by varying the radius ratio. So, again let us say like I mean if I draw this this rectangle, and let us say this rectangle has an area of 100 nanometer square, right. So, this is 10 nanometer and this is 10 nanometer. So, length is let us say 10 nanometer and width is 10 nanometer, right. So, this is 100 nanometer square area, and you have been given like two different colors ball. One is like red color ball which is having like 2 nanometer let us say, and another is a green color ball. This is red and this is like let us say green or blue color, let us say blue color ball which is also 2 nanometer. Okay. And now you have been asked to fill this rectangular area by these two balls, and you have been given the freedom you can arrange them in arbitrary way. So, when you started filling up this area with this ball, like I can arbitrarily put like one red ball, one blue like blue ball and red blue like that. Now, red blue like this, I can fill like this way. Now, once I fill like this way, so I see that there is a void which exists between these two balls. Now, instead of the 2 nanometer balls, if I increase the diameter of the red ball, let us say this is now 4 nanometer and diameter of the blue ball is now 4 nanometer. So, what will happen? Now, again if I fill this area with this 4 nanometer red ball and 4 nanometer blue ball, then the amount or the space of the void will now decrease. So, this is called the packing of the sphere. And this packing of the sphere in the case of the material science, they lead to different kind of crystallinity. So, you can get a tunable packing geometry or tunable crystallinity by varying the radius ratio. So, by changing from 2 nanometer to 4 nanometer of the red ball, or by changing from 2 nanometer to 4 nanometer of the blue ball, I can change the way they pack with each other. I can change the crystallinity of the system. That is one of the major advantage once you go to the nano domain. Tunable characteristic length scale by varying the radii but keeping radius ratio constant. Similarly, in this case like let us say I have changed the radius of the red ball from 2 to 4 nanometer and the blue ball 2 to 4 nanometer. So, in the first example the radius of the red ball to the blue ball is 2 by 2, that is 1. In the second case when I increase the radius it is again 4 by 4, 1. So, the radius ratio is same, but you can also make radius ratio different. I can increase the red ball ratio to 2 to 10 nanometer, and I can keep the blue ball ratio as 2 nanometer. So, in that case the ratio will be 5:1. So, if I change the relative radius ratio between the two sphere, so then also we can change the packing, we can change the characteristic length scale. So, these are some of the advantages we have learned from the inorganic self assembly of the nanoparticle. Now, all this example translate to the organic nanoparticle self assembly also. Here also if we make a donor nanoparticle and an acceptor nanoparticle, we can self assemble them and we can change the diameter or the radius ratio of the two different sphere, we can change their packing geometry, we can change their characteristic length scale. And also this organic nanoparticles, they are fabricated in the water or aqueous system, that is why it is a greener route of fabrication. Now, this organic solar cell like polymeric solar cell, they are made in the organic solvent like chloroform, but in this nanoparticle they are fabricated in water. So, that is basically a greener route of fabrication, and one can make the nanoparticle from any polymer possible which dissolves well in an organic solvent, but does not dissolve in a water. So, this method is also a versatile technique. So, because of this advantage, like organic nanoparticle has been used extensively in fabricating different kind of solar cell. Now, types of organic nanoparticles, what are the different types of organic nanoparticles are possible? One of the very common example is the engineered carbon nanomaterials like carbon dot, like graphene dot. Okay. Other organic materials, fluorescent organic nanoparticles, like organic nanoparticles can be luminescent or fluorescent, that means they can emit light. So, they will be useful for making LED or laser. Water soluble organic nanoparticle. So, the organic nanoparticle can be water soluble. So, the advantage is that like you can use it for drug delivery system, you can use it for bioimaging. Starch nanoparticle, again starch is carbohydrate like, so carbohydrate based nanoparticle, you can encapsulate any kind of drug inside the starch nanoparticle and use it as a drug delivery agent, and metal organic frameworks. So, these are all like different examples of the organic nanoparticle system. Now, once we go from the macro level or the micro scale to the nano scale, the fabrication process or the synthesis process is also different, that we call a nanochemistry. Now, let us say if I come from the giraffe to this creature orangutan, to this cat, to this swan, to this cat. So, what is the difference between these different creatures? Their size. Now, we have seen that their habit, their lifestyle, everything is different. So, similarly, if I start from a macro system and if I gradually reduce the dimension and go to a nano system, right. So, then their properties will also be completely different. So, that is called size effect. So, it is the smallness of the size which give rise to some of the very weird properties in the nanoparticle system, which usually we do not observe in the bulk system. For example, like if you take an quantum dot. Now, for example, I have this laser pointer, okay, or like let us say you take any chalk which is used in writing in the board. Now, this chalk is a 1 centimeter chalk. If I make it a white color chalk, if I make the chalk half, make it a half a centimeter chalk, it will still be a white color chalk. If I again like make it half, like let us say I make it like 0.5 centimeter or 0.25 centimeter chalk, again it will be like white color chalk. But if I have a like 10 nanometer scale chalk and if I make half like 5 nanometer chalk, then the color of the chalk will be different. If I take a quantum dot like cadmium selenide CDSE, which has a diameter of like let us say 8 nanometer, and if I reduce the diameter to 6 nanometer, then the color will change from red to blue. If I go to 2 nanometer, then the color will change to green. So, basically we can change the color or their optical properties by simply tuning their radius. So, that is tremendous achievement actually. So, that means that in a similar system, without changing the compositional element, just by changing the size or the ratio or the radius ratio or the radius, we can change their optical properties, and which is not present in the bulk system. What is the reason behind it? Is that we call size effect. You may call it as a quantum confinement, or you may call it as a quantum effect. Reason for delaying studies, the organic nanoparticle versus metal nanoparticles: low melting temperature, lesser thermostability, then limit the methods for their synthesis and applications, and believed that no size effect is manifested in organic nanoparticles. Now we know that there are a lot of advantage of using organic nanoparticle system, but how we can make this kind of system? So let us look at their preparation and synthesis methods. Now some of the factors which have to keep in mind when selecting any method is that their particle size. So that means what are the ultimate size we are looking for? Size distribution. So this is also an important parameter. Okay, so like let us say I have a 10 milliliter of solution and which is filled with the nanoparticle. Now out of that probably 10 millions of them has 100 nanometer diameter, 2 million of them has 10 nanometer diameter, 1 million of them has 1 nanometer diameter, and like let us say 4 million of them has 4 nanometer diameter. So there are nanoparticle in the system, but they are dispersed or polydispersed in their size. So that is called polydispersity. On the other case, let us say I have a 10 ml solution and each and every nanoparticle which exists in the solution has an exact diameter of 10 nanometer. So that is called a monodispersed solution, and this phenomena is called the size distribution. So whether the size is a monodisperse or whether the size is a polydisperse. A quantitative factor to characterize the size distribution is called polydispersity index or PDI. So if the polydispersity index is very small, then it is a monodisperse solution, and if it is very large, then it is a polydisperse solution. Now depending upon our ultimate goal or the application purpose, sometimes we need a monodisperse solution, sometimes we need a polydisperse solution. So there are methods to characterize whether a solution is a monodisperse or whether a solution is a polydisperse things. Like dynamic light scattering is a method, or TEM or transmission electron microscopy is a method which is used to characterize that whether a method is a monodisperse or a polydisperse solution or dispersion. Stability of the synthesized system, that is also very important. Let us say today I make the nanoparticle dispersion and within 1 hour all the system has been collapsed, that we do not want. Once we make it, let us say I wanted to keep that solution for 1 month or for 1 year. So the stability is also very important, and solubility, whether like I mean this is a dispersion, colloidal dispersion, or whether it is a solution, that also is very important. So that depends upon the particle size. So whenever we prepare or wherever we synthesize the material, so all of these factors has to be kept in mind. So in today's lecture we have discussed about like different methods or what are the factors we have to keep in mind for the synthesis or the preparations of the nanoparticles. Now in the next lecture we will discuss like what are the different physical methods and the chemical methods which is available in the literature for fabricating this organic nanoparticle system and how they can lead to some useful application. Thank you.